All right, so last time we stopped at a discussion of molecular orbitals as it relates to the allylic system. And so if we have an allylic system, we know we have 3 p orbitals, one on each carbon of the allylic system, right? If we start with 3 orbitals, how many molecular orbitals do we have to end up with? Nope. Nope. 3. Orbitals are conserved. You cannot destroy orbitals. You can just hybridize them. Okay? Hybridize them and form molecular orbitals. So orbitals are conserved. So if we start with 3 p orbitals, we have to end up with 3 molecular orbitals. Now, as I have these orbitals drawn, there's something that's not correct about it yet. What do we know about a p orbital? It's not just an elongated figure 8. What else is there that I'm not drawing yet? So if I draw a p orbital, is that it?
No.
What else do I need? No, electrons occupy the orbital. Orbitals can exist without electrons. Orbitals are really nothing more than like rooms in a hotel, right? I mean, you can have a room that has nobody in it, right? So electrons are just like the people. So in this particular hotel room, this P room, right? What am I missing up there? Is the top and the bottom identical? My signs, that's right. And we usually just take care of that by shading, right? Okay, so I've got 3 of these p orbitals, and I'm going to combine them in a way to get 3 molecular orbitals, right? And the easiest thing in the world to do is you've just got 3 molecular orbitals that go up in energy. That's easy. All you got to do is figure out how to draw a horizontal line 3 times, right? But what do those orbitals look like? We talked about this last time. What does this lowest energy orbital look like? If you were to draw it, what would it look like? It's not just a horizontal line. That's right. So psi 1 would look like just like that. And how many electrons can I put in that orbital? 2. We can have no more than 2 electrons in an orbital, right? Now we move up to psi 2. What does it look like? Right? Okay, so I'm going to have, and what's here? That's the node, right? How do I shade? The tops? Is that how we were shading them last time? Is that how we did it? Think so? You know so? Okay. Let's look back. Yep, you were right, right? One is, they have red and blue. And why do I know we have to do that? Why do we have to have the shading like this? Because the node in the middle, right, is where it's all canceling out, right? So we know that it has to be that way. So that's psi 2, of which I can put up to 2 electrons in. And then psi 3, how does it look? How can I take those 3 p orbitals and combine them to look? Sandwich. Ice cream sandwich. Alternating.
No, it's got 2 nodes.
It's got 2 nodes. That's right.
You add a node each time you go up.
Where are the nodes?
Between. Yeah.
Right? And again, we can add 2 electrons there. Now, if I'm talking about an allyl radical, how many electrons do I get to populate in those orbitals? 1? an allo radical. The radical has a lone electron, but how many other electrons are involved in the pi system? 2, right? Remember, an allo radical is this. So there's 2 in the pi bond, 1 in the radical. So I can put 2 electrons here, 1 electron here. This can be called the SOMO, singly occupied molecular orbital, but it's also a non-bonding molecular orbital. This is the bonding molecular orbital. Everything is bonding. This is non-bonding, or the SOMO, okay? What if I have a radical cation? How many electrons am I going to be dealing with? 2, right? So everything's bonding, right? So it's good. What about the radical anion? That's right. So is it stable? Yeah. I've got 2 in the bonding orbital, 2 in a non-bonding orbital, no problem. What about if I wanted to generate an allyl 2- anion? So this is bonding, non-bonding, and this is what? Anti-bonding. And what happens when we start to occupy an anti-bonding orbital? What does it mean to be anti-bonding? It starts to tear the molecule apart, right? That's exactly what it means. If you put electrons in an anti-bonding orbital, it starts to break bonds. That's what's going to happen. It's exactly what happens in an SN2 reaction. When the nucleophile comes in from the back, what is it populating? Those electrons are going to the anti-bonding orbital, which breaks the carbon-leaving group bond. That's exactly what's happening. And that's a good demonstration of why when you start putting electrons in an anti-bonding orbital, things start to fall apart. Okay? Fortunately for us in organic chemistry, this is about as difficult as the orbitals get. Okay? You just deal with the frontier molecular orbitals. Notice we've only dealt with the pi system. We haven't dealt with the sigma system because the sigma system really doesn't do a whole lot of chemistry in these types of reactions. Okay? So we can largely ignore them. So let's finish up what we were discussing. Okay? So here's an example of our allocation. And we said that an allocation should be stable, right? Because we've got 2 electrons in the bonding orbital, no electrons in an anti-bonding orbital. Everything should be peachy cream, right? So if you look at an allocation, you've got structure A and you've got structure B, which are nothing more than resonance structures of each other, right? And if you looked at the energy of A by itself and you looked at the energy of B by itself, they would be equivalent in energy, but they would be higher in energy than the overall hybrid cation. Why? Resonance. That's exactly right. This is an energy diagram illustrating that resonance actually does lower the energy of a system. Okay? And so we can see a lot of examples of resonance stabilization. For example, we've talked about this in the past. Benzene is a perfect example where it looks like you've got 3 double bonds. They are in conjugation with one another, and the hybrid is actually lower in energy than having 3 double bonds within a molecule, okay? And that's because of the resonance energy. Notice we say that half the positive charge is on this end, half the positive charge is on that end. And so if we were to have a nucleophile attack the allocation, which carbon would it prefer, the one on the right or the one on the left? Or the carbon on the right, the carbon on the left? You'd get a 50-50 mix, right? Because they're equivalent. And so it just goes to show that both carbon atoms on the ends actually have the positive charge, if you will. Let's do a quick little throwback exercise here. Assume standard workup where needed, but tell me what we're going to get in each one of these reactions. Take 2 minutes, work with your partners, answer these questions. Do I need to turn the light off? What do we make in the first reaction? A Grignard, right? So we take chlorobenzene. We're reacting it with magnesium. Diethyl ether is our solvent because we can keep it dry. And what does a Grignard look like? And the carbon, right? That's right. MgCl, right? What halogens can we have here? Yeah, just anything but fluorine, right? Okay. The chloride is a more difficult one to make. As you go down the periodic table, the halogens get more reactive in the Grignard reaction.
Why not the explosive?
No, it's not explosive. It's just very non-reactive, which is actually very good for you, right? Because Teflon is a fluorinated hydrocarbon. You can actually take stir bars and you'll use those to make your Grignards, and you don't make Grignards on your stir bars. Okay? So it turns out that fluorine's not very reactive in these types of reactions. Can I get it to react? You bet I can, but it's not very easy to do. Okay? So the reactivity in the halogen series is as we go down, the reactivity increases. Chlorine is not as easy to do. That's true. Most people like to work with bromides. Iodides are just typically more expensive to purchase, so bromides are kind of the happy medium. So this is A. So if we take A and react it with, what am I doing, formaldehyde? How is that formaldehyde? Yeah. No. This is formaldehyde. That's ether is the solvent, right? What's the product going to be? It's going to be a primary alcohol. We're going to end up with, after workup, that molecule, right? So tell me how that works. How's the mechanism work? In the magnesium chloride bond?
No, like, I'm talking about to the carbon.
Oh, okay, so the magnesium carbon bond. Okay, very good.
Goes to the oxygen.
To the oxygen? To the carbon?
Yeah.
Don't guess.
Yes.
Yes, all right.
Oh, yeah.
And so we end up forming a carbon-carbon bond. And that's what you end up with as an intermediate. And then you work it up with water. Usually we dump these over water and ice just to keep things cool and under control because the ether will tend to boil as it liberates heat. in the quench, and so that just makes it nice and convenient, and so you end up with a primary alcohol. Okay, very good. Question 3. We've got acetophenone, which is a ketone, plus something gives me so what is the conversion here? We're going from a what to a what? We're going from a ketone to a tertiary alcohol. What do I need to do that? Okay. Alkyl aluminum, or alkyl lithiums, I mean. We don't need lithium aluminum hydride, because that would just give me a secondary alcohol. But I'm getting a tertiary alcohol. How do I know I need to have something like a Grignard? I'm making a carbon-carbon bond, aren't I? So which Grignard reagent do I need? Nope. Pardon? Ethyl magnesium bromide will work. Because if you look at this, I've got a methyl group here. There's my carbon that was from my carbonyl, and there's the aromatic ring. So what I'm adding is an ethyl group to form that carbon-carbon bond, right? What else would have I accepted? I would have accepted ethyl magnesium bromide, ethyl magnesium chloride, ethyl magnesium iodide. I would have even accepted ethyl lithium. If you look at the product, notice that methyl group is already in my starting material. This carbon is what was the carbonyl carbon, and then the aromatic ring is already in my starting material. The only thing that's new there is the ethyl group. So how can I add an ethyl group and make a carbon-carbon bond? Use ethyl Grignard or ethyl lithium. That would work, okay? So all of those things that I just described would have given you full credit, okay? We just made a carbon-carbon bond. That's cool, right? It's the hardest thing in the world to do for an organic chemist. Making alcohols out of ketones and making amines and making anything with a heteroatom, for all practical purposes, is a piece of cake. The tough part is how do I take these small molecules and link them together to make a bigger molecule that I need? Carbon-carbon bond formation is what everybody focuses on in organic synthesis because it's the tough part. That's a bit of an overstatement, but it is what people sit and scratch their head about all the time. How do I make the carbon-carbon bonds that I need? What about the last problem? What do we get? A Grignard? How do I know it's not a Grignard? There's no magnesium on the board, right? What is there, though? So I'm starting off with the bromide plus 2 lithiums. The solvent is diethyl ether, and I get 2 products. So what are the products that I get? Okay. Yep, and what else? And lithium bromide. And you know that these reactions work because lithium bromide is not soluble in diethyl ether. And so as the reaction occurs, you see this white salt fall out of solution. You filter it off very carefully, not using a filter paper like you all would use, but a very special apparatus to filter under vacuum. And then you would have a solution in diethyl ether of the cyclopentyl lithium. Okay? And then you could go and do whatever you wanted to with it. Okay? Does that all make sense? Any questions about it? The arrow pushing for the lithium reaction, it's actually not very easy. It's a free radical mechanism where you're adding electrons one at a time. So usually what we do at this level is just recognize how to do the conversion. Grignard formation is not as easy as magnesium just slipping in between the bond. It's actually a surface type. This is all surface chemistry. It's very difficult to describe.
Do we need to make it like, I highly doubt it. We have no mechanism at this point. He said, just picture it kind of like this. He's like, but that's not how it happens. Just
We will get into that kind of stuff if you decide to go to graduate school and take a higher level organic course. But
Isn't there another organic course out there?
no.
On my flow chart.
On your flow chart said intermediate? No, we got medicinal chem.
There's no more.
What is now medicinal chemistry used to be intermediate or organic. And it wasn't very popular with people because it was essentially mechanisms to the nth degree. And people liked the medicinal part of it better, so we just killed that part of it and went with the medicinal. All right, so let's continue on in chapter 13. We're going to talk as far as we can today about some resonance, conjugated dienes, and stability of conjugated systems. I told you last time to review your resonance structures. So today we're going to see how well you are with your resonance to start with. So we're going to do a little bit of a review. Question 10, can I draw a resonance structure for that?
Yes.
And how will I draw that resonance structure?
The double bond.
From here to there, right? All right, very good. So I can move those electrons, and I would end up, so they actually drew it out, CH, CH, CH3. So I would move from here to here, and where does my cation go? Right there? That's right. So which of those resonance structures then would be the major contributor? The one that I just drew, and why? That's right, because it is allylic, just as the other one is, but it's also tertiary. So that is the major contributor to the overall resonance hybrid. How about 11? What can we do? You sure? Pardon? I can. I can take this pi bond and I can move it to the positive charge, which would put a lone pair on oxygen and a positive charge on this carbon. So would the resulting resonance structure that I just described be more stable, or this one? Why?
Because carbon didn't have a charge. The other one, carbon had. Well, no, the oxygen negative and carbon is positive.
Yeah. Are you sure? Now, in terms of thinking about it from charges, carbon can handle a positive charge better than oxygen. That's true. But this resonance structure has, everything has an octet. Everything in the resonance structure that we would have drawed, drew would be not having an octet, right? Can I draw resonance structures for 12? You'll say no. How many vote for no? How many vote, yeah, we can? The no's win. We cannot draw resonance structures for that. Why not? The charge is not in resonance or in conjugation with the pi system, right? We have a pi system that is completely isolated from that positive charge. However, if you were to generate this, a reaction would occur. And what would that reaction be? A reaction will occur. A reaction is the movement of an atom, right? Just by itself, something will happen. What will happen? Hydrogen will leave. Might leave somewhere and go somewhere else. What's that? A hydride shift or a rearrangement, right? What kind of cation do I have? I have a secondary, so that you need to follow the cardinal rule, right? And what can happen if we generated this secondary carbocation is one of these hydrogens would shift as a hydride and give the carbocation here. Then you would have resonance, right? And so that would be a more stable carbocation, even though it would still be secondary. You would not get a hydride from here shifting because that wouldn't give you any stability, right? How about 13? Okay, so what do? I would move a lone pair from oxygen to the carbocation and form a pi bond there, right? Which one would be more stable, this one or the one that we just described? The one we just described, because everything would have an octet. How about 14? Can I draw a resonance structure? I cannot draw a resonance structure. It is. That is absolutely true. However, I could probably get a hydride shift, and then it would be right next to the oxygen, which could then form a double bond.
So does the charge or radical have to be in the allylic position to a double bond for anything?
That's a good way of thinking about it. Yeah, you have to be in such a way that you can actually overlap with the pi system. Yeah. So that all you're moving is electrons. How about 15? Can I draw a resonance structure? I can. I can push this pair here and form a double bond. How about 16? I could do that. If I move from the double bond to the oxygen, that would give this oxygen a negative charge, but that would put two pluses on the same carbon. Is that likely? Not particularly likely, right? But I could do that. I wouldn't be breaking any of my arrow pushing rules, but that's not particularly likely. Putting two positive charges right on the same atom, not too good, right? What else could I do? I could make a triple bond. That's right. So I could take a pair, move here, and make a triple bond and put a positive charge on oxygen. And so that would actually be the major contributor, because not everything here has an octet, but everything in the cation that we described would have an octet. And how about here? The reverse, right? We can actually push from here to oxygen and have the carbocation. All right, very good. So let's skip some of those and get to some questions. Which carbocation is the most stable? Yep, B is the correct answer. Now tell me why. It's allylic and it's tertiary, right? So this is a tertiary carbocation, which should be fairly stable, but it's not allylic. This is allylic and tertiary. This is allylic, but secondary in either resonance structure that I draw. And then this is a vinyl carbocation, which is not very stable at all. Okay? So don't forget your resonance rules, right? You always want to have resonance structures with more bonds and fewer charges or more stable. This is more stable than that. Yes?
This is an embarrassing question, but what does allylic mean?
Allylic. We talked about that on Wednesday. What does it mean? We have a system like this. That would be the allylic carbon. It is the atom that is directly attached to an alkene. Okay, so that's the allylic position. Does that make sense? Okay. So we don't want charge separation, right, if we can avoid it. We want an octet, if at all possible, for things that are in the second period, right? And resonance structures that place the negative charge on the more electronegative atom are more stable. So for example, if we look at this structure, we notice that we have the negative charge on carbon. We can draw a resonance structure that puts the negative charge on oxygen. This is the more stable resonance structure and therefore the major contributor. However, we're going to learn in an upcoming chapter that even though this is the major contributor and the more stable resonance structure, the chemistry really occurs here. And we'll learn why that's the case. So you can't ignore minor contributors to a resonance hybrid. Okay? Which of these four resonance structures contributes the most to the overall picture of this molecule? Pardon? You think A? How many people think A? How many people think B? You guys are not brave on a Friday morning. You got to wait. Huh? C and D. All right, a lot of you think D. It actually turns out A is the correct answer. Now, why is D? Most of you thought D. Why is D not the correct answer here? It would explode? Okay. I know what you're saying. Yeah. The charges are closer together. That is absolutely true, and that's not an unreasonable thought. But what does D not have that A has for every atom? An octet. Octet rule really rules here, to use the two words in the same sentence. Okay, so if we look at this, right, carbon does not have an octet. But if we look at A, yes, there's charge separation, but every atom has an octet, right? And so how did we get to that? You push these electrons here to form the double bond. You take these electrons and move here to move the double bond here, and then you push the pi bond onto the oxygen. So yes, you have charge separation, but everything still has an octet. And so that's why A outranks D in terms of the most in the overall picture. All right. Let's start talking about conjugated systems a little bit more. We've already talked about the conjugation that we get in an allocation, an alloradical, and an alloanion. But that's just one thing that we need to discuss. If we look at some examples, okay, we have several opportunities in which we might think we have conjugated systems. For example, here with 1,2-propadiene, this is not a conjugated system. Why is it not? It's got 2 pi bonds. What's that? Okay, that's true. But any time I have 2 pi bonds, that should have a conjugated system, right? No. Okay. It doesn't have resonance. Some place for the electrons to go. That's true. Why is there no place for the electrons to go? Why do I not have resonance? It is all pi bonds. Well, there's sp. Let's think of the hybridization. You bring up a good point. What's the hybridization of this carbon? That's sp. That's right. So I have an sp connected to 2 sp2s, right? So if I have a pi bond between these 2 carbons, how is the pi bond on these 2 carbons? 90 degrees. Yeah. Well, it's a linear molecule. That's true. But the pi orbitals are here between carbons 1 and 2, and between 2 and 3, they're like this. And when you have this 90-degree business, what do we call that? What's the mathematical term? Perpendicular is one term. It's not the term that I like to use. It's called orthogonal. Okay? And it turns out that they don't talk to each other. Because if you think about it, the orbitals do not touch each other at all. They have to be kind of like this to touch one another, right? When they're like that, that's right. There's no overlap of those orbitals. And so this is just what we call a cumulated system, which we'll talk more about.
What was that word you used?
Cumulated. Orthogonal.
And that means perpendicular?
Pretty much. Yeah. No, it has nothing to do with that. So here we've got 1,3-butadiene. It is a conjugated system, right? We've got the pi bond, single bond, pi bond kind of motif that we've been seeing an awful lot, right? 1,3-penadiene, either where you have Z or cis or trans, I should say. We have a conjugated system here as well. Pi bond, single bond, pi bond. Here, we do not have a conjugated system. We have pi bond, single pi. Can't conjugate. 1,4-cyclohexadiene, same thing. We have pi, single pi. So there's no way that these 2 pi bonds can actually communicate. However, octatriene, if you look at it like this 2,4,6 octatriene, you've got pi, single pi, single pi. This system from carbon 2 to carbon 7 is conjugated within those carbon atoms, okay? And so this molecule is actually pretty stable. Okay? In fact, maybe one of your favorite foods, the reason it has its color is because of its conjugated system. If you like carrots, they have an orange color because there's a lot of pi bonds that are actually conjugated, okay? And it means that it can absorb light easily and give off a color, okay? So isolated dienes are things like this where you have a pi and then some number of sigma bonds pi, but it's not the pi, sigma pi kind of motif that we've been talking about. That would be what we get in a conjugated diene, pi, sigma, pi. And then these cumulines that we talked about earlier, right? If you'll see it, you've got the orbitals drawn here. So the p orbital here is coming out of the plane of the board and behind the plane of the board, whereas this set of p orbitals are in the plane of the board. And so they're 90 degrees or orthogonal to one another, and they don't talk, so to speak, okay? Now, 1,3-butadiene, or these conjugated dienes, they can be in what we call the S-trans or the S-cis conformation. We've talked about cis and trans before. What does trans mean? On opposite sides or across. Okay, I'll buy that. What does cis mean? On the same side, right? All right, works pretty well. Now, what's this business with S and S that we see here? It's not stereochemistry in the sense of R and S. What does S-trans and S-cis mean? Pardon? Not S orbitals, but you're getting close. Sigma. That's right. It is, these two carbons are trans because of how they rotate around this sigma bond. These are cis around this cis bond. And we know, what do we know about rotation around a cis, or a sigma bond, I should say? We have relative free rotation, okay? Not completely free, there are energy barriers, but we can rotate around a sigma bond. And so we can rotate this 1,3-butadiene such that the two groups are trans to one another or cis. Now, they say that this is fast, and it is, and they show the equilibrium as almost being equal. But what do you know? The trans is like 99.9% of all of it, okay? However, it turns out that on Monday when we start talking about Diels-Alder chemistry, okay, which you'll need to read about this weekend, okay, when we start talking about it, the S-trans diene can't react. The S-cis does. And so you have to be able to rotate to get that chemistry to occur. If you were to take this molecule and go over to the NMR, you would see all of this in the trans conformation by NMR. You would see none of it in the S-cis. So little we can't detect it by, or at least by the NMR techniques that you all know about. Okay? Now, if we think about these conjugated dienes and we start looking at bond lengths, things start to get kind of interesting. So if you look at the bond between carbon 1 and 2, we notice that the bond length is 1.34 angstroms. If we look at the bond length between carbons 2 and 3, we notice that the bond length is about 1.47 angstroms, okay? And 3 and 4, of course, being symmetrical, it has to be exactly 1.34 angstroms as well. Now, if we look at this for comparison's sake, and we look at ethylene to kind of mimic the alkene part of the molecule, we see that we have a bond length of about 1.34 angstroms, okay, as you might expect. But what's interesting is the bond between carbons 2 and 3, notice there's a substantial difference in the bond length. Can you explain that for me?
Because the hybridization is a little bit different.
What hybridization?
And like coming off that carbon versus coming off carbon 2 to carbon 3.
Okay.
There's sp2, and then
What do we know about the size of an sp3 orbital versus the size of an sp2 orbital? It's larger, right? So if I take two small things and I put them together, am I going to get something larger than if I take two large things and put them together? No. Right? If I give you two short pieces of string and two long pieces of string, There's no way to take the two short pieces of string to get to be longer than the two long pieces of string. Same kind of thing here, right? And so that accounts for this. But also, if you think about it, right, this is a situation, if you look at this bond, it's kind of in between a double bond and a single bond. Resonance structure tells us that this bond should be shorter than a typical single bond, because we can draw resonance structures that actually put a double bond between those two carbons, right? And so we know that from resonance theory as well. But yes, Aubrey, you were right. It's all about overlap of the different orbitals, and so I'm not going to go through the whole list, but if you have two sp3 orbitals overlapping, you get about 1.5, or just a little over 1.5 angstroms. If you put an sp2 and an sp2 together, you get at about 1.47, and if you put two sps together, notice you get about 1.37. And even though they are all sigma bonds, that does not mean that they're all the same length, and it has to do with the fact that the orbital size changes, and again, it's kind of like putting strings of different sizes together, okay? Now, you can prove that conjugated dienes are actually more stable than isolated dienes by doing a very simple experiment. This is an experiment like you all did in Gen Chem. Remember when you did the calorimetry experiment? You were measuring the amount of heat that was given off by something, right? And you were able to figure out a bunch of thermodynamic junk, right? You guys used a coffee cup calorimeter, right? It's cheap, it's easy. You go to Starbucks, you get a couple coffee cups and a thermometer, and you're ready to go, right? However, we can't do something quite that simple in organic chemistry because 1,4-pentadiene and 1,3-pentadiene are liquids that kind of dissolve styrofoam to start with, okay? So we have to have a special calorimeter, but the concept is exactly the same. So if you imagine taking 1,4-pentadiene and you adding hydrogen across the double bonds, you get to what compound here? Pentane, right? If I take this conjugated diene and I hydrogenate it, I get to the same compound, right? So if this tabletop on the energy scale is pentane, if I can measure the amount of energy that it takes to get to that level, I can tell whether or not something's more stable, right? So the thing that gives off more energy must have been higher in energy to start with, right? It's kind of like jumping off the Empire State Building without a parachute versus jumping off your bed. Okay, we can measure the heat difference pretty easily, all right? So if you look at it, 1,4-pentadiene gives me 61 kilocalories per mole in this reaction. This reaction only gives me 54 kilocalories per mole. Right? These are just isomers of one another. Same number of carbons, same number of hydrogens. We're adding the same number of hydrogens, but I'm getting different amounts of energy. So that must mean that this molecule is starting from a higher point. It is less stable because these double bonds are not talking to one another, if you will. They're not in resonance. Okay? Now, if I was to show you this reaction on an exam and I asked you, is this reaction endothermic or exothermic, and I didn't give you these numbers, you would tell me that it has to be exothermic. Why? Breaking bonds by itself is always endothermic. I'm creating sigma bonds. I'm breaking weak pi bonds, which takes energy, but I'm gaining, which are not high, opposite of high. Low energy. They're very stable. So I'm getting very stable sigma bonds at the expense of weaker pi bonds. So on an exam, you should be able to look at these types of reactions and tell me whether or not overall these are going to be exothermic or endothermic. You can't tell me this kind of stuff. This is experimental data. But your chemical intuition should be such that you would say, I know this is going to be an exothermic reaction. I'm making a lot of sigma bonds from something that had some pi bonds. Okay?
Would you expect us in theory to know that 1/4 of the diene would make a little more energy?
Absolutely. Yeah, absolutely. Why do you think? What do we know about resonance? What does it do to the stability of a molecule? Does it raise it or does it lower the energy?
Oh, it lowers the energy.
Yeah, it increases the stability, but increasing the stability means to really lower the energy, right? So this has to be at a lower energy than this one. And that's how I know that that has to be the case. Can I Could I, just by looking at this, know approximately this difference? No, that's an experimental number that I need to know. But I should be able to derive that kind of information in a pretty straightforward manner. Okay. If you look at a conjugated diene, we can draw several resonance structures, right? We can draw the resonance structure here. We can draw this resonance structure where we have charge separation, and we can draw resonance structures where we have this charge separation. Which of those three is the major contributor? The first one. And why? Okay, no charges and full octet, right? So that's why. But the hybrid really shows that we have some of these pi bonds are kind of delocalized over the system, right? And so that lowers the overall energy and increases the stability. So this weekend, I will pincast Chapter 12's problems. I will post to YouTube a short video of stuff that we're going to talk about on Monday. We will come in Monday and we will start by just having a little bit of an overview of the Diels-Alder reaction and some kinetic and thermodynamic addition chemistry to conjugated dienes. So read over that, and then we'll get in our groups and work on the inverted lecture. Inverted lectures were due today, so please turn them in up here on your way out. Have a great weekend.